Today we're going to talk about noise in antenna systems. Let's start by considering a receive antenna scenario. Your receive antenna, there's a particular signal that you are interested in receiving. Let's make it blue. It's coming to your antenna with some radiation intensity, and you are receiving it. Cool. Does that mean that you get to detect the information out of it, and is it a usable signal? We don't know, because there is noise surrounding you in your environment being emitted by a lot of different types of sources. And whether or not that signal that you get from your desired source is usable kind of depends on how strong it is in relation to all of these other sources. Those sources can be electromagnetic radiation from the sun. They can be noise generated by the starters of automobiles. They can be generated by the arcing of lightning, heating up the air around it. And you can also have interference from other intentional human-made artificial radiators, like a radio tower or something. Any of these things, or all of them, are present in a typical radio system. All of the red ones are noise, which is either natural or unintentionally human-made, and it's random. Most of the noise that we're going to talk about, and this is a simplification, but this is also an undergraduate antenna class, so that's fine. Most of the noise that we're going to talk about is additive, white, Gaussian noise. Additive means that the noise power gets added to the desired power. So I'm going to say PS for signal. It's not getting multiplied by anything. It doesn't have anything fancy going on. It's just getting added in. White means it has a constant frequency spectrum or a spectral density. Meaning that on average, or at least within the bandwidth of your system that you care about, the noise is not more at one frequency than it is at another. It's equal at all the frequencies. Gaussian means that the amplitude of the noise, let's say it's voltage, but also goes for the current, is a Gaussian random variable. On the other hand, interference doesn't work the same way. I'm not going to write the description of interference in yellow because that might make it hard to read. But interference is made by humans intentionally. It might be another radio communication signal that happens to be in your band that you care about or something like that. But it is a radiator that humans made to radiate, and it's just inconvenient for you right now. So in the presence of noise, we're not going to worry about interference in this class. We're just talking about noise. In the presence of noise, how do you detect the signal that you do want? Well, if I make a plot of noise power versus time, it's going to look something like this. It's kind of got a pretty reasonable average level that you can identify, but it's very wiggly, and sometimes it's greater than that, and sometimes it's less than that. Now that average level is what we call the noise floor. And in order for us to detect a signal that we want to see, it needs to be appreciably above the noise floor. The reason for that is, obviously, if your signal is about the same size as the noise floor, you won't be able to detect it because it'll be lost in the noise. But even if it is, let's say, that big, how do we know if this peak is the signal we want or if it's noise like that one? This one is pretty clearly above all of the noise peaks, so that is a detectable signal, I would say. It's pretty common to need a signal-to-noise ratio, which is usually abbreviated as SNR. A common signal-to-noise ratio that you might need could be 10 dB or 20 dB. So the signal-to-noise ratio is defined as the power that you receive from your desired signal divided by the noise power. Now this received power from your desired signal you get from the Friis equation or the radar range equation. And the noise power you get from noise power equals KTB, where K is Boltzmann's constant. B is the bandwidth of the system. B is the bandwidth of the system, and T is the system noise temperature. Okay, but what's the system noise temperature? Well, if it were a resistor, that noise temperature would just be the physical temperature of the resistor. But antennas have a slightly more complicated situation because, like we talked about before, they receive noise power from objects in the environment, and that gets included in the noise temperature of the antenna. Every object that has a temperature above 0 Kelvin radiates electromagnetic energy because of the random motion of its constituent particles. And all of those things contribute to the noise temperature of an antenna. So the noise temperature of your antenna is a weighted average of a quantity that we call brightness temperature as a function of angle from the antenna's point of view. And it's weighted by the gain of the antenna. So all of these objects in the world, some of them are generating electromagnetic radiation because of their physical temperature, including things like the sun, which is very hot, so it's actually a pretty strong radiator of radio frequency noise. And some things are generating electromagnetic noise through some other means, like a car starter, which has a pretty high current and involves some arcing, and so that generates electromagnetic noise. Or lightning, which has pretty much the same characteristics, except more so. So all of those things contribute, along with the physical temperature of the ground, of the sky, even empty space isn't really empty and has a noise temperature of its own. It's just very low. And it's called cosmic background radiation. that gets included in your antenna noise temperature. So even if you're in space surrounded by nothing, you're not really surrounded by nothing. But for a physical object, that brightness temperature depends on the physical temperature of that object and also a property it has called emissivity, which is a measure of how well electromagnetic radiation can actually leave the object or whether it gets trapped inside. It has to do with the reflection coefficient of waves entering and leaving the object. So in this class, we're going to provide brightness temperatures for things. You're not going to be expected to calculate it. But just so you know, part of it is the physical temperature of the object, and part of it is its electromagnetic properties. So, okay, let's say that I know the brightness temperature of the world as a function of angle. And I also know gain of my antenna, so I have now calculated my antenna temperature. Does that mean I know my system noise power? Not exactly. There's more to it, because your antenna is connected to the receiver through a transmission line, which has loss. It has an attenuation constant, alpha, and it has a length, L. So at the terminals of this transmission line, your receiver sees an effective antenna noise temperature. Your book uses T(a) for that, even though we use T(A) for the actual noise temperature of the antenna. That's confusing to me, but that's what we got in the book, so I'm going to go with it. So the effective noise temperature of the antenna is what the receiver sees after all the antenna noise properties have propagated through the transmission line. So we've got the noise temperature of the antenna, which we calculated from that brightness temperature integral. So that times e to the minus 2 alpha L, that's just a power attenuation due to propagation down the line, plus we have TAP, which is the antenna noise temperature at its terminals due to the antenna's physical temperature. That's also times e to the minus 2 alpha L, plus a contribution from the transmission line itself. So T0 here is the temp of the transmission line. And then that gets multiplied by 1 minus e to the minus 2 alpha L. And let me break this down and tell you what TAP is. That, the noise temperature at the antenna terminals due to the physical temperature of the antenna, is 1 over the antenna's radiation efficiency minus 1 times the antenna's physical temperature. Okay, so now we have the noise temperature of the antenna as it appears at the receiver terminals of this transmission line that the receiver is connected to. Are we done? No, we are not done, because the receiver itself also has a temperature. So the total power, the total noise power in this system is K times T(a). That's the noise temperature of the antenna as seen from the receiver terminals, so looking into the transmission line, plus the noise temperature of the receiver itself times the bandwidth. So both the antenna and the receiver have a contribution to the noise power. But once you know this noise power, you can put that in to your required SNR value, and that'll tell you the minimum value of receive power that you need in order to successfully do your radar detection or your communications link.